So today's concept is 13th group elements. So in the examination point of view, group elements are very important from inorganic chemistry. So among all group elements, 13 and 14 group elements are very important. So we know that what are the elements we have in the 13 group element: boron, aluminum, gallium, indium, thallium. So the first important point what we need to remember is oxidation states of these group elements. So here two kinds of oxidation state will exist, +3 as well as +1. So the boron, as we go down from the boron to thallium, the plus one oxidation state complexes are more stable. This is because of a net pair effect. So now the boron is more stable in the +3 oxidation state as well as aluminum. But if you see that in the case of thallium, so thallium +1 is more stable than thallium +3. Okay, so this is about the group elements oxidation state. And another point, if you see the crystal structure of boron, so boron will exist in the form of B12. So the structure is a icosahedral. So this question asked many times, icosahedral in examination. It's very important, you have to remember this point. Now I'm directly going for the boron hydrides. So now we have like B2H6, B4H10, then we have B6H10, then B10H14. So we have 4 borons, A, B, C, D. So the question is, we have to find order of Bronsted acidity. This is the first one. The second one is, which is more reactive, reactivity towards electrophiles. So there is a question on this Bronsted acidity, but there is no question on this reactivity towards electrophile. So we can expect a question on this. Okay, so we know that what is a Bronsted acid. Bronsted acid is nothing but a proton donor. Proton donor is a Bronsted acid, and Bronsted base means proton acceptor. Okay, now we need to identify which is a strong Bronsted acid here. So, and then another thing we need to remember, the stronger the Bronsted acid, then in that case we can use a weak acid. If it is a weaker Bronsted acid, if any compound is showing weaker Bronsted acidity, then we have to use a strong base. So this can also, they can ask in examination point of view, among these 4, so where we have to use a strong base to remove the proton. So first we need to see how, from where the proton is coming. We'll take B2H6 diborane. Now we have a doubt that whether to remove this hydrogen or this hydrogen. Always remember, the bridged hydrogen will remove only bridged hydrogens. Okay, so in case of boron hydrides, deprotonation means only bridged. So you can question yourself, why only bridged, why not the terminal? So we know that this bond is the 2 center 2 electronic bond, but this bond 3 center 2 electronic bond. Okay, and if you see the stability wise, so this is more stable, but here the stability is not there. So because this is a 3 center 2 electronic bond, if this is a 3 center 3 electronic bond, then this is also equally stable. I mean, it will be stable. I am not saying equally or less or more, it will be stable, but this is the 3 center 2 electronic bond. So because of that, this hydrogen we can remove it, and that too in the form of H plus. So when we are removing the hydrogen here from the H plus, then what will happen? There is a like this I will write BHB. So we are using some base, and now we are removing this hydrogen in the form of H plus. H plus is coming out, so then now what is left? B minus. Okay, now first I will talk about the reactivity towards the electrophiles. Okay, then we will talk about the Bronsted acidity. Okay, now so if the negative charge is there on the anything, like if X atom is there, so we have a negative charge on that, and X plus is there. So which one is more electron rich? So X minus is more electron rich and X plus is electron deficient. So where more negative charge is there, the electrophile goes and attacks there. So this is the fundamental things we know that. So because of that reason, and the reactivity towards electrophile is associated with the Bronsted acidity. So we have a more number of these bridged hydrogens, so that will be more, that shows more Bronsted acidity. So we can also say that if number of borons are more, that is having a more Bronsted acidity. And if you see the Bronsted acidity here, so D will be more Bronsted acid, then C, then B, and then A. So this is the Bronsted acidity order. And then we have a reactivity towards electrophiles. So if you see the reactivity towards electrophile, since it is a more since it is the highly Bronsted acidic in nature, the more negative charge will develop on this, right? Because of more negative charge is developing on this, the electrophile goes and attacks to this first. So the electrophilic reactivity also same in order. And now, so where we need to use a strong base and weak base? So definitely for Diborane we have to use a strong base, because that is a less Bronsted acidic in nature. So any electrophilic reactions like Friedel-Crafts alkylation, acylation, and halogenation, any reactions, if they ask in examination point of view, by giving any of these boron hydrides, just see where more number of borons are present. So that is a more that is stronger Bronsted acid, and that develops more amount of negative charge, and that is more reactive towards the electrophile. So this is the concept of Bronsted acid and reactive towards these electrophiles. And if they ask in the nucleophile reactivities, we just make it opposite. So whatever the electrophilic reactivity is there, just we do opposite, then it will become nucleophilicity. And another thing here, I want to explain the structures of halides. Okay, so we'll take AlCl3. So what is the AlCl3 structure? So AlCl3 is having two types of structures. In solid state, it exists as a octahedral structure, but in the liquid and vapor state, it exists as a dimer. Okay, so aluminum, we have octahedral shape. This is in the solid state, but in the liquid state or solution or solid liquid and as well as vapor state, it exists like Diborane structure. And this point group is very important. This belongs to D2H point group. And then we have another complex, that is Al2 C2H5 4 H2. So this also exhibit same kind of structure like Diborane. So here the hydrogen will be bridged hydrogens, and remaining ethyl groups will be terminals. So these structures, just remember, in examination point of view, it is important. And we know that Lewis acidity order of BF3, BCl3, BBr3 and Bi3. So among all these things, so Bi3 is a stronger Lewis acid, then BBr3, then BCl3, then BF3. It's all because of overlapping. When we have a boron and fluorine, here we will see a strong overlapping because this is 2p orbital and this is also 2p orbitals. So because of the strong overlapping, the electron density will distribute around the molecule. That's why this is the least Lewis acidic in nature. So where we have a Bi3, so here boron is having 2p orbital and iodine is having a 5p orbital. The overlapping will not be that strong here. So because of that reason, this is a strong Lewis acid. And another thing we have here, boron nitrides. Boron nitride. This we show by Bn, and this we can prepare by taking B2O3 plus, by treating this boron B2O3 with the 2 moles of ammonia, it produces 2 molecules of Bn plus 3H2. So why I am explaining this one is, so we know the graphite, right? Graphite. So the structure of graphite resembles this one. Sorry, the structure of Bn, boron nitride, is almost equal to the graphite structure. The differences and the structure wise, these two are same, but the graphite is a conductor, but this is not a conductor. Okay, this is a metallic conductor. Bn is a metallic conductor and the graphite is a electronic conductor. So just from the boron nitride point of view, we just need to remember only 2 points, that is Bn structure resembles graphite and it's a metallic conductor but not electric conductor. And another important point in this 13 group element is alum formation. Alum means what? Double salt formation. We can write double salt formation. So among boron, aluminum, gallium, indium, thallium, only aluminum, gallium, indium, these 3 forms double salts. But boron and aluminum will not form a double salts, because to form a double salt, the condition is the size should be in the medium. It should not be so small and it should not be so much high. If you see boron, the size is very small, and if you see the thallium, size is very big. So because of this reason, this boron and thallium will not form any double salts. So this can also be a possible question, that why boron and thallium will not forming double salt formation and why remaining are forming double salt formation. So because of the size of the boron is so small and the size of thallium is so big. So because of that reason, double salt formation is not taking place. And next we see the Lewis acidity of Diborane. Okay, so when we treat Diborane with any Lewis acid, sorry, this we cannot be called Lewis acidity, the reactions of Diborane with Lewis acids. Okay, so Lewis acid breaks Diborane into 2 parts. It can be a symmetric cleavage, or asymmetric cleavage. So how the symmetric cleavage we see? Symmetric cleavage means H H H H. Symmetric cleavage means it gets symmetrically like this. So here we can say 2 moles of BH3. So asymmetric means so one will takes here, so another will takes here, so one forms a BH4 plus, another forms BH2 minus. This is unsymmetric cleavage. So there are some bases, Lewis bases, which favors symmetric cleavage, and there's some Lewis bases which favors unsymmetric bases. So when the size of the Lewis base is small, okay, so this prefer unsymmetric cleavage. I will explain why. When the size of the Lewis base is large or bigger, that prefer symmetric cleavage. So now we'll take example of 2 examples. We have NME2 and B2H6 plus NH3. So among these two, which favors a symmetric cleavage and which favors unsymmetric cleavage? The size of NH3 is small, whereas the size of NME2 is bigger, and which is having bigger size, that favors symmetric cleavage, and which is having small size, that favors a unsymmetric cleavage. So first we'll talk about the small. So what is the unsymmetric cleavage? Unsymmetric cleavage is nothing but BH4 plus and BH2 minus. I think this is negative and this is positive. So now this we have BH2 and 2 moles of this ammonia and goes and fit here. Since the size of the Lewis space is very small, so 2 ammonia can accommodate inside. Okay, that's why here we are getting a, when we have a Lewis base which is having a smaller size, then we'll get an unsymmetric cleavage. So in final product of unsymmetric cleavage will be where we have a BH2 plus, so there 2 moles of ammonia comes and attacks to boron, so it forms this one. Since the size of the Lewis base is bigger, this is favor for the symmetric cleavage. Okay, in symmetric cleavage we will be ending up with 2 moles of BH3, and here only one NME2 can accommodate, and finally we'll get, I'm writing here, finally we'll get this compound, 2 moles of this compound. So when we have a small base, in that case we will get this compound. When we have bigger base, in that case we'll get this compound. So this is about the how the Diborane gets cleaves. Till now they have not asked in examination point of view about this, but we can't we can't leave any question like that. And there are some more concept, some more topics are left on this 13 group element. I will be making another video for that. I hope you understand this video. If you have any doubts for this video, you can write in the comment box, and if you like my video, you can subscribe and you can share to your friends also. Thank you.